Good day and welcome back. This will be the first part of our discussion on directional derivatives. Now, up to this point in the chapter, you've hopefully noticed that we are very closely paralleling the discussion of differentiation that we went through in Calculus 1. First introducing the idea of partial derivatives, computing them, interpreting them geometrically, and then we moved on to investigate things like linear approximation and the chain rule. All, at least big picture, are familiar concepts. But in this section, we are going to take a small deviation and look at something that's new to our scenario of having multiple variables, these directional derivatives. In this first video, we will introduce the concept of a directional derivative. In the second video, we'll work through some examples and think about how we can quickly and efficiently compute directional derivatives. And in the third video, we'll investigate several applications. But to get started, let me take you back to how we originally defined those partials f sub x and f sub y. So recall, at a point x naught comma y naught, we define the partial derivative with respect to x to be this limit as h approaches 0 of a difference quotient. And the big takeaway of having this limit of a difference quotient is to note that the partial derivative with respect to x is a rate of change in the x direction. So if you are sitting at a point in the xy plane, and from that point you move in the direction determined by the x-axis, i.e. in the direction of the I vector, the partial derivative with respect to x measures the rate of change of our function in that direction. And we have a similar idea for the partial with respect to y, which we originally defined as the limit of the difference quotient, where note in this case it's really a rate of change measured in that y direction. So if you're sitting at some point in the plane, it's measuring how the function changes if you travel in a direction that's, say, parallel to the y-axis. And this leads us to really kind of a motivating question. We can find the rate of change in the x direction, in the y direction. How about in some other pre-specified direction? That is, if we're sitting at this point x naught, y naught in the xy plane, and we move in the direction given by some vector u, can we measure the rate of change of the function of two variables in that direction? Which leads us directly to the idea of a directional derivative. And let's see if we can illustrate this rate of change in a picture. So we're thinking in blue, we have our surface z equals f of xy, and we want to know if we're at the point x naught and we travel in the direction of this vector u, how does our function change? So similar to what we did with a partial with respect to x or a partial with respect to y when we interpreted them, we're going to draw a plane that cuts the xy plane at u and see where it intersects the surface. So I'm going to think of this plane going through the vector u, and we're going to see where does that plane cut our surface. And it looks as though by inspection that it's going to cut our surface kind of along a nice curved line. And if we're at this point x naught, y naught, and we trace up to the corresponding point on our surface, let's go ahead and call this P, where P would correspond to the point x naught, y naught, z naught, with z naught being the function output associated to inputting x naught, y naught. So in this plane, at the point P, that curve we've drawn will have a tangent line at the point P. And I'm going to go ahead and define this tangent line as t. And that leads us to the desired observation. So the slope of this tangent line at P is the rate of change of our function in the u direction. Which is a directional derivative. So symbolically, if we were to take this one step further, the directional derivative of f at a point AB in the direction, and note this is key, a unit vector u is defined as follows. So the directional derivative of the function f at the point x0, y0 in the direction of a unit vector u. So it's a mouthful to get it all out, but compactly we have the following notation. And this is defined similar to a partial with respect to x or y. It's a limit of a difference quotient. So f of x0 plus ah, y0 plus bh, minus f of x0, y0, all divided by h, where these quantities x0 plus ah and y0 plus bh is indicating we're calculating that rate of change if we go in the direction of the unit vector given by a comma b. And this is the directional derivative as long as the limit exists. And it turns out that we typically will never use this limit definition of the directional derivative, just like we have really not used the limit definition of the partials with respect to x and y. But what it does is it gives us some intuition, and in our next video it will allow us to see how to compute these directional derivatives. And the observation I want to make to finish up is that directional derivatives are in fact familiar objects, at least in several specific scenarios. If you wanted to know the directional derivative in the direction of the unit vector I, that's actually the partial f sub x. And similarly, if you look at the directional derivative in the direction of the unit vector j, that is simply the partial with respect to y. So even though directional derivatives are a new idea, in a sense, they are quantities that we've been working with through the last few sections. So that completes our introduction of the directional derivative. In the next video, we'll investigate the directional derivative from a purely computational perspective. Stay tuned and take care.